topic of discussion is called rationalizing the denominator. This is what those words mean, to rationalize the denominator. It means that mathematicians don't like the square root of numbers in the denominator of a fraction. So if I had 5 over the square root of 3, it's not an acceptable answer. My teacher, when I was young, used to say that we couldn't allow radicals in our basements, the denominator. Couldn't allow a radical to hang out downstairs. Here's what we mean. If I have the square root of 17 over 6, what I essentially have is the square root of 17 divided by the square root of 6. That's inappropriate. I can't have a radical downstairs. The way I get rid of that is to multiply by 1. And I do it in the form of something that will allow this denominator to become a whole number. And most often it's going to be just multiplying by whatever the denominator is. And that's not always true, but that will always get you a good answer. Sometimes not a simplified answer. I do it because the square root of 6 times the square root of 6, I know to be, especially from the last lesson, to be 6. Again, the square root of a number times the square root of a number is just that number underneath. So I've gotten rid of the radical downstairs. All I have to do now is multiply 17 times 6 in the numerator and put that underneath the radical, and that product is 102. I'm done. I rationalized the denominator. I don't have a radical in my basement anymore. It's the proper form of writing the expression. It's kind of like this. It's kind of like saying that that's not an acceptable answer. If you gave me an answer of 2/4, I would be expecting you to reduce that to 1/2. That's kind of like what we're doing here. Again, mathematicians, we say we don't like radicals in the basement. I can't leave it like this. I multiply by 1 in order to rationalize the denominator. When I rationalize a denominator, I only have to get rid of the radical. I don't have to do or think about this 8. I need to get rid of the square root of 2 and make it become a 2. I do that by multiplying by 1, and the form will be a square root of 2 over square root of 2, because this product right here is equal to 2 itself. So what I have then downstairs is this 8 times, again, the square root of 2 times the square root of 2 is 2, so I essentially have a 16 in the denominator. I'll go ahead and finish that. And upstairs, now I just need to multiply where I can. So I have 3 times the square root of 5 times the square root of 2. That's just equal to 3 times the square root of 10, because the 5 times 2 is 10. And I'll put that over in this numerator, and we've rationalized this denominator. There's no radical downstairs. When rationalizing this denominator and thinking about that square root of 32, it's a little too much to just multiply top and bottom by the square root of 32. What I'd rather do, and let's first write this as 2 separate radicals. What would be simpler to do is to come up with something I could multiply the square root of 32 by that would make this a perfect square. And I know that if I multiplied 32 by 2, I would get a 64. And the square root of 64 is just 8, because 8 times 8 is 64. That would be the simpler thing to do in this problem than to multiply by the square root of 32. If I did that, I'd have to simplify the problem in the very end. In the numerator here, I'm going to have the square root of 10a. And in the denominator, again, I'm going to have the square root of 64, which is just 8. And here's my solution. No radical downstairs. I'd just like to share something with you about what our book does for this problem. I wanted to show you my way, and I wanted to show you the book's way. The book discusses the fact that in this denominator, the square root of 32 is 2 times 2 times 2 times 2 times 2. And let's not pay too much attention to the 5a up above. And what the book does is they discuss the fact that we know that the square root of 2 times the square root of 2 is 2, or a pairing here is equal to 2, and that's a pair. And so we have a lone 2 out here, and that's how the book helps you to decide that you've got to multiply by the square root of 2, top and bottom here, so that that lone 2 here has a partner, and when you multiply them together, you get just 2. Either way, you decide. And when we deal with cube roots and fourth roots and fifth roots or whatever, sometimes this is much easier to do. As a matter of fact, the next problem that I'm going to do will show an example of that. Here's our next problem, but we're going to take the cube root and rationalize the denominator. That's a little bit different. So what I need to suggest that you do is first break apart the numerator and the denominator. And I'm going to suggest that since the denominator is a 9, that you write it as its prime factors. And remember now, because we're looking for a perfect cube, I need 3 pairs to be able to take the cube root. So what I'm going to do in this case is I'm going to multiply by 1 using the cubed root of 3, because I know that 3 times 3 times 3 is 27, and the cubed root of 27 is 3. It's like saying the square root of 2 times the square root of 2 is 2 products. Well, the cubed root of 3 times the cubed root of 3 times the cubed root of 3 is 3. So I had to multiply by a single, if you will, cubed root of 3 in order to make this denominator just a 3, to get rid of the radical. And then upstairs, 2 times 3 is 6, underneath the radical, representing the cubed root. I've rationalized the denominator. There's no radical downstairs. This problem's complete. Another problem involving cube roots. I have the cubed root of 2y in this denominator. I'm going to multiply by the cubed root of 2y times 2y here, because I have to get those factors 3 times in order to be able to simplify it. So essentially, let's go ahead and show this twice underneath the radical. That's what I'm going to multiply by, so that I have a pairing, I shouldn't call it a pairing, a group of 3 that are underneath the radical. The cubed root of 2y cubed is 2y. And so that's why I choose to use 2y twice here, since I have 2y once and I'm taking cube roots. Well, if I do that, then I have to put that in the numerator as well. And now it's a matter of just multiplying what's underneath the radicals together to get our numerator. So I have the cubed root of 5 times 2 times 2, which is 20, x times y, which is xy squared. And I can't do any simplifying with this because this doesn't have a perfect cube that factors into it. The x is not raised to anything greater than 3, or 3 itself, nor is the y. So I'm complete upstairs. It's simplified. I no longer have the radical in the basement. I have rationalized the denominator. We're going to rationalize a denominator where the indice is a 4 now. A little bit more difficult possibly, and I'm going to take a little bit different approach. I'd like you to remember something before we do this problem. I'd like you to remember that if I took the 4th root of x to the 8th, y to the 12th, our rules for exponents said that that's the same thing as taking x to the 8th, y to the 12th, and raising it to the 1/4 power. And ultimately then, this 8 times 1/4 gave us 8 over 4, or x squared, and 12 over 4, or y cubed. And as long as these numbers were divisible by the indice, 8 divided by 4, then I could just simplify this and call this x squared, and 12 divided by 4 is y to the 3rd power. So what I'm going to be doing here is I'm going to be looking to make this number divisible by 4. So I need to up it by 1 to make it an 8. I'm going to look to make this number divisible by 4 also. So I need to up it by 1 also to make that a 4. And then finally, I have to find out what I need to multiply 8 by to make that a perfect 4th. Well, this is how I'm going to recognize it. First of all, I'm going to go ahead and put the 1 upstairs all alone. And I'm going to recognize that 8 is 2 times 2 times 2. So it looks like I'm missing a factor, one factor of 2, to have 4 multiples there. And again, don't forget I'm missing a factor of x and a factor of y. So what I'm going to choose to do here, let me get rid of this, is I'm going to choose to multiply by the 4th root of, I need a 2, so that I will have 1, 2, 3, 4 of those. I need an x to the 1st power. I'm going to put the 1 there, because this 7 and this 1 adds to be 8. and I want that to be x to the 8th, so the 8 is divisible by 4, and I'm going to multiply by y to the first as well, because this 3 and this 1 adds to be 4. If I do that downstairs, when I rationalize the denominator, I have to do it upstairs. And so finally, I have, let's go ahead and put our numerators together, but that's just 1 times all of that. So I'll have the 4th root of 2xy up in the numerator. In the denominator, the 4th root of 2 times 2 times 2 times 2 is 2. It's out of the radical. X to the 7th times x to the 1st is x to the 8th, and the 4th root of x to the 8th is x to the 2nd. The radical is gone. Y to the 3rd times y to the 1st is y to the 4th, and the 4th root of y to the 4th is just y. And I've rationalized the denominator again because I no longer have a radical in the basement, and I can't simplify what's upstairs any longer. This problem's all done. We're now going to rationalize a radical expression where there's a binomial in the denominator. The last few problems that we've done have had monomials there. The way we rationalize the denominator when we have a binomial is to multiply top and bottom by the same thing. So in other words, we're multiplying by 1. But what we're doing is we're multiplying by what's called the conjugate of this denominator. Well, the conjugate of a binomial like this is one where the terms are the same. I have a 5 and a square root of 2. But I change the sign that's in between these terms. Here I have a minus sign, so the conjugate of that expression is a 5 plus the square root of 2. Well, if I multiply it on the bottom, I have to multiply it on top by the same thing, so that I'm multiplying by 1. And then whenever I put binomials in here, I always put parentheses around so I don't forget to FOIL those. Now, what I'm going to do is I'm going to FOIL this binomial downstairs, and I want you to just see that I always get rid of my radicals here. Because 5 times 5 is 25. Then the outer terms are 5 times the square root of 2. But the inner terms right here are a minus 5 times the square root of 2. Those always collect to be 0. And then the radicals therefore are gone. And then right here I have a minus times a plus, which is a minus. And the square root of 2 times the square root of 2 is just 2. I can be promised or guaranteed to always lose my radicals when I multiply a binomial by its conjugate, because the outer and the inner terms add to be 0. They collect and they disappear. And then the last term is always, and it doesn't matter where my radical is, it could actually be my first or my last, but when I multiply a square root by the square root of the same value, I always get that value underneath. So in this case, no radical left in the denominator. I have 23. Up here I just have to distribute the 4 times this 5, and that's equal to 20. And the 4 times the square root of 2 is exactly that, 4 times the square root of 2. I'll bring it over here, 20 plus 4 times the square root of 2. This is my answer. I've rationalized the denominator because I no longer have a radical in the basement. The conjugate of this denominator is 7 minus the square root of 3. This problem doesn't differ much from the last one, but it does at the very end, and that's why I've chosen this problem. So I need to multiply top and bottom by 7 minus the square root of 3. And again, please put the parentheses around. And I always like to look at my denominators next. So I have 7 times 7, which is 49. And essentially, I just have a minus square root of 3 times the square root of 3, which is 3, because my middle terms disappear. In the numerator, 2 times 7 is 14, and 2 times the square root of 3, with the minus sign brought along, is what's left up there. Downstairs, keep the numerator. Downstairs, 49 minus 3 is 46. If I stopped here, I haven't simplified this expression, and that's your dilemma. You have to watch for this. Because these two terms in the numerator have a common factor of 2, I'm going to factor a 2 out. And what happens is I have 2 times 7 minus the square root of 3. I did that because I saw that the number 46 down below, it has a 2 as a factor. As a matter of fact, it's 2 times 23 will give you the 46. And what I can do now is I can remove these common factors of 2. They're equal to 1. 2 over 2 is equal to 1. And my answer to this expression should really be 7 minus the square root of 3 over 23. When it's simplified, I've rationalized the denominator. I don't have a radical downstairs, and I simplified it. I need to watch to do that. Another problem where I want to multiply by the conjugate to rationalize the denominator. So I've got the square root of 3 minus 2 times the square root of 7. So the conjugate is just going to have a plus sign in between. So I'll come on over here and show that I'm going to multiply by 1 using the square root of 3 plus 2 times the square root of 7, top and bottom. Your dilemma in this problem is just going to be careful multiplying. With all these radicals involved, it can get a little messy. So let's go ahead and look at the denominator first because it's the simplest. The square root of 3 times the square root of 3 is 3. Again, please remember, I don't care what they are, this outer and this inner will combine to be 0. That's why we use the conjugate to do this, so that we can get rid of those inner and outer products. And so finally I have left here a minus times a positive, which is a minus, 2 times 2, which is 4, and the square root of 7 times the square root of 7, which is 7. So my denominator, after I simplify it, looks like it's going to be 3 minus 28, or a negative 25. I'll get to that in a minute. Let's take a look at the numerator. The square root of 6 times the square root of times the square root of 3 is the square root of 18. The square root of 6 times this 2 times the square root of 7, I'm going to put the 2 out in front, and then the square root of 6 times the square root of 7 is the square root of 42. Next, a minus 3 times the square root of 5 times the square root of 3 is a minus 3 times the square root of, square root of 5 times the square root of 3 is the square root of 15. I'm almost running out of space, so I'm just going to show. And then a minus 3 times the square root of 5 times a plus 2 times the square root of 7. First the signs. Minus times a plus is a minus. 3 times 2 is a 6. And the square root of 5 times the square root of 7 is the square root of 35. I'm afraid I've run off the board. I'm going to rewrite this. I have in the numerator the square root of 18 plus 2 times the square root of 42 minus 3 times the square root of 15, and this is what I might have run off the board, this last term. A minus 3 times a positive 2 is a minus 6, and the square root of 5 times the square root of 7 is the square root of 35. All of that is over 3 minus 28. And 3 minus 28 is a negative 25. And I'm almost done. The only thing is this expression right here. I've got to come back and look at it and see if by chance any of those terms can be simplified. And this one is one that I know can, because a 9 divides into 18. And the square root of 9 is a perfect square. I can't think of any numbers that are perfect squares that divide into 42. Numbers that are perfect squares are numbers like 4, 9, 16. None of those go in. 4, 9 doesn't go in here. 4, 9 doesn't go in there. So it's only the square root of 18 that can be reduced. The square root of 18, remember, is the square root of 9 times the square root of 2, and the square root of 9 is 3 times the square root of 2. So my last step here, and I've pretty much run out of room, is to replace that term right there with, I guess I can repeat this, with 3 times the square root of 2, and everything else stays the same. All of it is over that negative 25. I don't believe I can reduce this because the only factors of 25 are 5, 25, and 1. And none of these have the same factor that is divisible by 5. So I can't reduce this. This problem is complete. I'm going to conclude section 5, Rationalizing the Denominator, where we've been working with radical expressions where our goal has been to get rid of the radicals in the basement with this problem. I've got in the denominator here the square root of a minus the square root of b. The conjugate of that would be the square root of a plus the square root of b. So we'll multiply top and bottom by that conjugate. Again, I just changed this sign to a plus sign. Again, if you have binomials all over the place, would you please enclose them in parentheses so that you don't forget to FOIL them. All right? The denominator is always the easiest, so I always go to that first. The square root of a times the square root of a is a. Again, right here and right here, add to be 0. Finally, a minus times a plus is a minus, and the square root of b times the square root of b is b. It does look as though the denominator is not going to contain any radicals. We've gotten rid of that. And finally, in the numerator, be very careful with this. The square root of a times the square root of a is a. Here I have the square root of ab. And here I have the square root of ab. That means there's 2 of them. 2 square roots of ab. So I've collected those 2 like terms. Didn't write those down individually, but went ahead and collected them in my head. And then the square root of b times the square root of b is just a positive b. This is complete. There's no longer a radical downstairs, and we've rationalized the denominator. We're going to go on to solving radical equations in the next section, section 6.